Welcome, all 9 people in the room, to Databases and Information Systems, Lecture 11, which is about linear classifiers and logistic regression. Welcome also to the 28 million people on Zoom and in front of the television. So we will talk about your experiences with exercise sheet 9, and there is number 10. Welcome. Vector space model and word embedding, slight introduction into linear algebra. Another reminder about the official course evaluation, which is also participation is at an all-time low, and today more linear algebra classification, linear classifiers, the perceptron. Very briefly, it's of historical interest, but nice intro. Here comes number 11, 12, 13, wow, 14. Welcome. And logistic regression is the main topic. And exercise sheet 11 is about classifying movies. 2 classes, funny and not funny. And you should do that based on the movie plots. And I see a rogue number here. And this, the new line is not correct here. This. Okay, and there's still a bit noisy in the room. Experiences with exercise sheet 10. I think this should be 10 here, right? And not 9. That was... maybe this time let me start by showing the master solution. So this was a light introduction. I will not recapitulate it, but just say what it was. Into linear algebra, exercise sheet, exercise 1 was just repeating the search engine from the second lecture, but not with an inverted index, but with just matrix vector multiplication. I basically showed it in the lecture. You just had to plug in BM25 scores, and then the results are the same, but you use linear algebra. The second task was more interesting, and that was, so here's the master solution for the sheet. So we have these embeddings, and I've showed them in the last lecture. This is just for every word, not for every word, but for over 100,000 words, a vector of dimension 300. And then we have these movie plots, which we also use today. So here for movies, today we use them with labels, funny or not. And now, just based on the movie plots, let's find similar movies. And so this is the command line similarity search. So I'm taking the movie plots as input and these embeddings, and let's just do it. And I'm also, as usual, because it's so useful, loading the approximate search so that I can easily select a movie. And one of the movies from the exercise sheet was Interstellar. I mean, I can even make a typo here. This is something we made for one of the exercise sheets. Convenient even in this context. Type something, you get the movie here, select one. And now I find movies that are similar to Interstellar. How is it done? You just take the movie plot here. For every word, if it's in that embeddings, you look up the embeddings, otherwise you ignore it, and you just sum them all up. And then you get one 300-dimensional vector for this movie. You do that for every other movie, and now you just find the most similar vectors and see what comes out. So Interstellar is about future of Earth, science fiction like movie, interstellar travel, and so on. So what do we have here? Young researchers travel into the future. Interstellar is also about time travel and so on. Apocalypse. Here we have aliens, deep, NASA scientists, also about space. Also here's nuclear war, Earth. So kind of related. And let's, what would be, another one that comes to my mind, Saving Private Ryan, which is a war movie. Let's look at that. Saving Private Ryan is about World War II. A lot of movies about World War II. And here the similar movies. This is also GI, World War II. And you might say, that's easy, but note, I mean, the machine has no concept here of which words are more important than others. So it's kind of surprising that it works so well. It just adds up all the words, no matter what they are. I mean, yeah, I think not all the words, there are no embeddings for the stop words, but for exciting, there's probably a word embedding for that. So it's surprising that it works. And let's, and just to see that it makes a difference, whether you use meaningful embeddings, which were pre-computed and given, and these are just, now you just have a random vector for each word. So each word, each pair of word is, it doesn't have to do anything with its meaning, whether the vectors are similar or not. They are all like equally dissimilar. And now let's do the same. Let's look at similar movies. This is Interstellar again. And now we have, you would have to read the whole abstract, but just from a first look, it's not about space travel. It's not about aliens. So here's another one, also not about aliens. So when you did the exercise sheet, you find that they are not very related. One important thing, that's why I'm showing this, random embeddings also work, and I think you should understand this. So let's just look at Harry Potter movies. There are a lot of them, and they all are called Harry Potter and something. So let's just take the first one here. And if I take the first one, so that's my query movie, I do get a similar movie here, even with random embeddings. And I'm just saying it now in one sentence, but try to understand it yourself. Even with random embeddings, this works if the words in these plots, if they use very similar words, like if they would use the exact same words, you would get this as the first hit, even with random embeddings, right? And for these Harry Potter movies, I mean, here you have, you see it, right? There's just so much repetition here. This is here and this is here. So if you sum the embeddings up for those two, you get the same vector. Think about it in case it's not clear. It was a very nice sheet with relatively easy technology. You get something which already works quite well. So very cool sheet. So impressed how much one can do with linear algebra. That was our first intro. Next two lectures are also about linear algebra. Really enjoyed this sheet, more straightforward than last two. As always, I admired the beautiful code templates, which are due to Sebastian. He puts a lot of work into them. Thank you. So with fast text embeddings, as I said, we didn't compute them, we just gave them to you. They're from Facebook. Results look like they make sense with random word embeddings, Look random, mostly, but not always. I just explained it. Fast text embeddings were faster. I don't think so. They were not faster than the random embeddings, right? They are faster than faster than exercise 1, maybe, but I'm not sure about that. Were we supposed to, in the lecture, I just used torch, cosine similarity for the exercise sheet. You should have implemented it yourself, but if you didn't, I think that applies to some people. It was for some of you first contact with PyTorch. PyTorch is a huge library. We did provide a cheat sheet for you. But still, you have to get used to it. And I think one of the things that maybe is a bit hard in the beginning, it's not mainly a linear algebra package, it's a deep learning package, and everything is a tensor. So a vector is a one-dimensional tensor, a matrix is a two-dimensional tensors, and then, so all the interfaces are more tuned towards working with tensors of possibly higher dimension. So linear algebra things are sometimes a little unintuitive. And that's a good observation. If you look a little bit closer, which was also part of the exercise, if you enter, now it was movies where kind of it's clearer what similarity means, Interstellar, other movies about science fiction, future space travel. What's really similar? If you take, I don't know, a movie like Inception, Fargo, but many of you don't know movies, so I won't talk more about this interesting aspect. One reminder, so the official course evaluation in the past, when the exercises were mandatory and we gave you 20 points for the evaluation, we always had a about 95% of the people filled out the evaluations. Right now it's below 20%. I even got a warning. So, of course, if you don't listen to the lectures, but also then you don't listen to this, and you don't follow the course really, you don't do the exercises, then you don't have to fill it out. If you follow the lectures, at least maybe do. Let me just remind you, so it's still, you should have gotten this link. And it still runs until Sunday, but after that it's just over. So if you are participating in this lecture in some meaningful form, please give us feedback and answer this question honestly. It's anonymous. Are you doing the exercise sheets? A little bit, not really, mostly. It's interesting. Okay, and we will try to, today after, I think we got some messages here and we will mail them and see. I think there are 1 or 2 people. Are there still people in this room who wanted to participate but couldn't for some reason? Can you show hands? Okay, nobody in this room, and it also filled up a little bit. Great. So, 15 past. We continue with a Danke Frank, with the actual topic. First half will be relatively lightweight, and I will go a little fast because it's easy, so that we have more time for the interesting stuff in the end. Today it's about classification, very important problem. Yeah, given an object, predict to which class it belongs, and no, there are not 2 examples. Example on the next slide. It's just I deleted 1 example on the next slide, and here's an example. So, yeah, we use movie plots. So again, movie plots. So now we have, that's the beginning of a movie plot. In a small island off the American coast, the Waterleys live in an old mill where a mystery, bloody being, and now the class, the label is, what genre is this movie? And yes, that's a horror movie. And kind of looks like, it doesn't say American horror movie from 1972, it just gives the plot. Otherwise it would be easy. But there are kind of hints here that it's not a comedy or romantic something, maybe combination. A starship crew in the 23rd century goes to investigate the silence of a distant planet's colony. Science fiction. 2 actors attempt to make it in the cruel world of showbiz without an ounce of talent between them. Comedy. So, let's assume you get a lot of movie plots like this and their correct label. And now you're supposed to learn just from the text what's the correct label. That's what classification is about. So, after this, maybe you're given 1,000 of this, and let me just quickly show you the data set we give you for the exercise sheet. So it also contains these, it's on the wiki. Here I'm accessing it from the file system. Data sets, and it's they are all our and it's movies, funny and not funny. Not funny means it can still be very watchable. Train. Yeah. So now you just have the movie plots in 1 line here, and here it says, is it a comedy or not? Is it a funny movie or not? Geography professor has divorced his wife. Funny. Okay. So, and you get these, and let's just see how many of these you have here for the training set. So just to learn, imagine your computer, you get 50,000 of these. And now you're supposed to learn from the text, predict the label. And now learning is done, and now you're supposed to predict. Now you get a new text which you haven't seen before. Professor Iris discovers a secret in an ancient stone, and when he opens the crypt, he revives. What's your guess? Genre? Which genre would you guess given this plot? Fantasy. Okay, interesting. Yeah, maybe fantasy, maybe horror. maybe comedy. So it's not so clear, right? Just from the plot. Okay, that's the problem. Quality evaluation is important. Now you have something that predicts. How do you measure it? With a single number or few numbers? And for that you have this training set for training. We already had that in the third lecture when we talked about evaluation. And then you have the test set. I mean, this concept you already know. These are different movies. You learn on some set on movies, you evaluate on another set, which you haven't seen. Let's just see. This test set is usually smaller. You want a lot to train, but also a meaningful number to learn. So you have 16,000 movies to evaluate. So how do you do that? So let's first talk about the problem when you have many labels, like for the genres, science fiction and so on. So what you have what's in the ground truth. So this is the set of documents labeled science fiction, for example, and what your algorithm predicts. Yeah, and these two sets, I mean, ideally are the same, but your algorithm will make errors. And then you can compute for each class the following: the precision, and let me just very briefly explain this. So you have for a particular class, for example here, this is the horror. So this is all movies which are actually horror movies, and this is what your algorithm says are horror movies. Yeah, this is what's meant by that. And the two are not the same. So what we have here, we have always three sets here. These are the movies which are actually horror movies, but your algorithm said something else. These are the movies which are horror movies, and your algorithm correctly identified them. These are movies which are not horror movies, but your algorithm said it's a horror movie, your prediction. And then you can compute these sets. So here we have, among my predictions, how many are correct. That's the precision. And I will say this very briefly. You have to think about it yourself, do the exercise to understand why it's precision recall. This is here from my predictions, how many are correct. And this is from the ground truth, from the horror movies, how many do I predict as horror movies. That's called precision, that's called recall. And then you take an average here, and you may wonder, why is this not precision plus recall divided by 2? You take the harmonic mean here. Let me just very quickly do that calculation. So what you do here, F1 is the harmonic mean, which means you take the reciprocals, 1 over p plus 1 over r, and you divide them by 2. And that's called the harmonic mean. Harmonic mean. And if you do that, let's just do the math here. If I multiply this by p and r, I get, I can do the following. Yeah, let me just do the following here. 1 plus p plus 1 over r. If I multiply both by p and r, then I get r plus p over r. P, that's just some very basic math, and if I plug this in here, then I get r plus p over 2, let me call it pr, and if I turn this around, then I have f1 is equal to 2pr over p plus r, which is, I think, exactly what's written here. So yeah, it's just the harmonic mean. You take the means of the reciprocals and then turn it around again. And this is something nice to prove. I think it has also been an exam question in the past. Try to prove it yourself. This is 100% if and only if these documents are the same. So if the algorithm always does the right prediction. If there's only one error, this thing here cannot be 100%. Okay. We will mostly talk about two classes today, and also for the evaluation, for the exercise sheet, it's two classes. So you will look at this for two classes. And there's more terminology, because one very often has two-class problems. So for two classes, you often call the two classes plus and minus, positive and the negative things. So for our exercise sheets, funny are the plus examples, not funny are the minus ones. So you have a certain property, is it fulfilled or not, funny in this case. And then your predictions partition the input into 4 sets. It's a partitioning. So each element now exactly has one property, and you just look at what is the prediction, what is the truth, and all 4 combinations. So you have the true ones. This is where the algorithm was correct. True positives. It is plus and is predicted as plus, or true negative. It is minus and predicted as minus. And the F ones are where your algorithm makes a mistake. So yeah, it is minus, but you say plus. That's a false positive. So this here says the first word whether it's correct. This says what it actually is. Now what you said, this here refers to the prediction, right? You said positive, but it's wrong. You said negative, but it's wrong. And when you do that, and this is useful for the exercise sheet, and you should know this, then, I mean, just look at it. We have precision and recall, then just refer to the precision and recall of the positive class. You could also look at it for the negative class, but for 2 classes you only look at 1. And just, so what you try to understand this, what your algorithm predicts is, well, it predicts the one which are positives, so that's what I just said. Here it's what your algorithm predicts, and which are indeed positives, but also where it predicts and where it's wrong. So this is, I think that's clear from this. So it's just this union, this, and the ground truth. You can also write it in terms of one of these 4. The ground truth is the one which are positive and your algorithm finds them, and the ones which are positive but your algorithm doesn't find them, and these are the false negatives. So this is something you should also know, right? Fn is, yeah, I mean, just look at this. This here is, yeah, that's the one which are predicted as positives. It's Tp and Fn. Yeah, I don't have to say it again. Okay, you need this for the... Just one thing about understanding, difference to lecture 2. So in lecture 2 we already talked about evaluation, training set, test set, and so on. And there we had, the ground truth was a set, the relevant documents. And let me just write that here, the relevant documents. And I had 2 slides about this. The relevant documents, but we computed the ranked list. Here the situation is the ground truth is a set, so I want to find these funny movies, and my algorithm also computes a set. It doesn't do ranking or anything. Whatever my prediction is, it will give me the set, says here the funny movies, the others are not funny. And you will, I'm sorry, in the future, when you do research work, when you write a project or thesis, people always, they sometimes say, I evaluated the precision and recall. You always have to say what these sets are on the previous slide. So if you want to understand what your evaluation did, always explain what these sets are and what the classes are. Then it's also clear what you evaluate. Okay, linear classifiers. So this was classifiers in general. You have a problem with 2 labels or more and you want to classify it, some basic terminology. We will talk about linear classifiers. So objects are vectors now, so it will be more mathematical now in d dimensions. We have exactly 2 classes, like I just said, plus, minus. And now we want to separate them by hyperplane. And a hyperplane, I will give the mathematical definition on the next slide. And for d equals 2, so the hyperplane just has one dimension less, and it's easy to understand for d equals 2. So let's just draw an example. If I'm in 2 dimensions and I have some points here and some points here, and then, yeah, this is my hyperplane. My hyperplane is the line. Space is 2-dimensional, the line is 1-dimensional. And you can, yeah, if you want to separate things in 3 dimensions, you can do it with a plane which has 2 dimensions. Now, of course, the points do not have to be separable. Maybe I have a minus over here, and what do I do then? I have a slide about that. And how this works is, the algorithms, we will look at 2 of them today, will find such a hyperplane, and then the decision will just be made, okay, for a new point, so I have a query point, and now, for example, here, and they ask what label is it, and I just look at, okay, on which side of the hyperplane is it? It's on the plus side, then it's plus. Okay, and this is, yeah, if you have a plane, it naturally divides things into 2 classes. The question is, can you also use this approach for more classes? I also have a slide on this. First, some basic mathematics, which you should know from a linear algebra course, but maybe you forgot. So a quick recap of a few things. 2 definitions of a hyperplane. And I used to prove that they are equivalent. I will not do that, but the proof is still there if you are interested. So that's one definition, which is maybe the more intuitive definition. And let me draw a bad picture for this. So let me just draw it in 2 dimensions. So you have here, so that's definition 1. So what do I have? I have some point on the, and maybe here is my coordinate system, and I have here some point on the plane. So this is my hyperplane here, some plane somewhere in space floating around. This is my hyperplane. I take one point, and that's my A here, that's my anchor point. And then I have 2 vectors in the plane, for example, this one, and let me call them H1 and H2. So here I have 2, because and this picture is in 3 dimensions. Yeah? So if I want to describe a plane in 3 dimensions, I think this is even something you might have done in school. I have an anchor point here, a point, and then I can write every point as this vector, this point on the plane, plus some linear combination of H1 and H2. So that's one definition. And the other definition is, which is, it's also not hard, and we will use that because it's not much nicer to work with. Let me draw it again here. The plane is defined by, I just have a normal vector, and I will call it W. W for weights, not for normal, because the components are weights or values, which we are going to learn. And the hyperplane consists of all points where W, the dot product, and let me say this again, this is the dot product here of 2 vectors, right? Dot product is a fixed value B. It's actually a very nice exercise to prove that these are equivalent. It's not hard, but we will just assume it just takes time if I do it now. And I think anyway you only learn it if you do it yourself. And we will use that definition. So a hyperplane, to define a hyperplane, you have a vector W in the full space. You have a scalar B, and then the hyperplane is just all points which fulfill that property. And this is the normal vector. And let me write so in that case, it's a little less intuitive. In that case, H is all points for which the dot product with this W is B. And please do ask questions anytime. Now we do some mathematics because we need it all the time. How do you compute the distance from a point to a hyperplane? So let's assume we are working always with that definition now. Hyperplane is all the points where for a given W and B, this condition holds true. And now I'm claiming that the distance of any point to this hyperplane is this. And let's prove this. And more than that, so this is always, because I'm taking the absolute value here, a non-negative number. If you take the absolute away, then this here, the scalar dot product minus the B tells you is this on the left or on the right side. I mean, that's not obvious, right? And let's prove this. It's a very nice proof and some recap on linear algebra. Let me just draw a line here and let me have my point. That's not the dot product, that's my point. So maybe let me not make it so thick. Or let me make it... come again? The B? Okay, the B is just... so this is a vector in d dimensions and B is a scalar. So these are the two values which define the hyperplane. You give me a vector and a B and they define a hyperplane. So that's definition 2. And I didn't prove that that is the same as this. So if I give me a vector, I give you a vector and a number, and then this defines a hyperplane, namely all the x's which satisfy this condition. Yeah, to really understand it, one would have to do the proof, but we now just take this definition. So this is my x, and this is my hyperplane here. So this is my hyperplane in 2 dimensions. So now my example here is in 2 dimensions, and this W is a normal vector. It's perpendicular to the plane. Now let me draw the following picture. Namely, let's take here the projection of, let me draw it perfectly. So this is a right angle now, and let me call this x prime. It's a very nice proof, and if you have trouble with this, you should definitely do it at home. That's the level of linear algebra you should know for this course, not more, not less. Let me take the normalized version of this, which is I divide it by its length. We did that in the last lecture. L2 norm of, which is Euclidean length. And then I can, then the distance, which is what I'm looking for here, the distance of x to h. Let me just name this r, and then I can write x as x prime plus r times w0, right? So this thing here, the length of this is r times, or this difference here, yeah, this is just, it's the distance. Let me just say that again. No, I didn't want the highlighter, I wanted the pointer. To get from x prime, I just have to, this is the projection of x, so I have to go away from here perpendicular, and I have to, if the distance is 5, I have to go 5 times the normal vector to reach x. So this is what this here says. Okay, and now, even if this was not 100% clear for you, you have to think about it at home. Let's just, as you do in mathematics, let's just take it for granted and proceed from here and try to prove it. And what could we do? Let's multiply it with w on both sides. And let's do some. So this implies, if I multiply it with w on both sides, then I get this times this plus r times this. And with a dot product, everything is linear, so you can pull normal multiplication in and out, so you get this. So nice thing about linear algebra, you can just do stuff and then magical things happen. So what's this? Do you have an idea what this is? From what is on the slide, you can say what this is. What do we know about x prime? So x prime is on the hyperplane, right? It lines on the line. So what do we know about this value? Yeah, it's b. I mean, the hyperplane is all the points where w times is b. So that's b. So it was a good idea to multiply with. And this here, okay, this also looks familiar, multiplying a vector with itself. It's almost, that is, yeah, I mean, let's just write the definition of W0. That was W divided by W, a vector multiplied with itself. We had that in the last lecture. It's just the square of its length divided by its length 1. Nice thing, you just do it. You don't necessarily have to understand. You could always ask for the geometric intuition, but let's just do it here. Yeah, and now we almost have it. So now I have, yeah, let me just write what we have derived. So this is b plus r times w, and this just says that, yeah, if I solve for r, then this is just x minus b divided by w, which is just what I wanted to prove. And if x is on the other side, I'm sorry, writing down here is a little bit harder, is on the other side, then I have x prime. Yeah, now I have to go to the other side. I have to go in the opposite direction of the normal vector. So the normal vector points to the positive examples, or at least that's how I define it. X prime minus r times, yeah, analogous. You can just do the same thing again, and then you will get this thing reversed here. So yeah, this is just to show you the level of linear algebra that you need, how you do it in principle. As usual, I mean, maybe you were convinced now by the individual steps. To really understand it, you have to do it yourself. There's no way around it. So please, it's also, yeah, typical exam question is to do this proof, parts of this proof or variants of this proof. So you should certainly understand this, but you have to do it yourself to fully understand it. Let's go on. One thing that's important, it's a bit annoying that to specify a hyperplane, I mean, let's go back to these two definitions quickly. This is intuitive definition. You specify a point on the plane and then d minus 1 vectors, but you have so many values which you have to specify, the a and these vectors. This is nicer. You just specify one vector, which is the normal vector, which also gives you a direction, this side, the other side, and this offset. Wouldn't it be nice if we wouldn't need this number? Then we only have one vector, and that's what you usually do in these tasks. And that's what this slide is about. And it's so that's our typical definition. So you have a vector and a scalar, and this is the definition. Now, let's look at this definition here. I just add one dimension, and now the bias is 0, which means this goes through the origin, right? It's a plane, yeah, H contains the origin. I mean, it's clear that it contains the origin, right? If you plug in the all 0 vector, yes, it's 0. Here, not necessarily. so contains the origin. And the origin is just the all zero vector. Yeah? So if I do that, then I can very easily prove that if my original vector is in this plane, then this vector is in this slightly different plane, where I've added to my normal vector one dimension here, and the value is minus b. And let's just verify this by taking this value here, so w times x minus b. So if this is 0, then x is contained in this set. Yeah? And let's just write it down. So that's this dot product minus b. And this is just the same as writing, just adding one dimension here, minus b here, and then 1. I mean, just convince yourself that this is the same. And this is, I want to write this by hand here, and this is just w prime times x prime. If I just, if I call this here x, and this here x prime. That's the formal way. What you can take away from this is what you can do if you want to get rid of the b, and again do it yourself to fully understand it. You have a problem, you have vectors for the exercise sheet, 300 dimensional vectors for example. Just add one dimension and give every vector in your input the value 1 in that dimension. So that's what you do here. And then you can search for a hyperplane with where the bias term is 0. And understand why it works. You add the additional dimension, and what happens that in your w vector, the value in that additional dimension will effectively the bias term if you would have solved the problem in the lower dimension. And this is the math. So that's a nice trick. So you should understand two levels. One way is how you do it in practice, and for the exercise sheet you just add a dimension and 1 everywhere, and why that works. And that's the mathematics, which is easy. Two more things. This is just to understand. So what if the data is not linearly separable? And let me just give you one nice example. So all the methods we look at today, and in fact most methods, also work if it's not linearly separable. They will also always compute a hyperplane no matter what. But here's a nice trick, and I just wanted to show it to you by an example. So let's assume so we are in R. So our points are just values, scalar values in R to the 1. And let's assume here I have -1, and I have -2, and here I have 1, and here I have 2. So I'm living in a very not so interesting one-dimensional world. And let's say I have, how do I draw them? Maybe in red, and maybe I have a plus value here, and then I have 2 minus values here. So a linear separator here would just be a value also. I mean, this can't be linearly separated, right? There's no way. I mean, you would need 2 cuts or intervals or something like that, but you just can't cut them. Of course, if all the minuses are one side, all the pluses on the other side, it would work. And now, by lifting it to a higher dimension, so let's just look at the function. Here's one function. And there are many functions which would do the job. So this goes from R to R2. And I'm just doing the following. Out of every point, I make it a one-dimensional point, I make a two-dimensional point. Same, and here I take the absolute value. So what happens now? Now -2 becomes, so I'm now transforming my problem in a more interesting two-dimensional world. And now minus 2 becomes the, let me also draw the 1, 2. And maybe you can already see it in your mind, becomes minus 2, 2 becomes 2 comma 2, right? So this is the, let me just write it here for clarity. This is the point minus 2, 2. This is the point 2, 2. And what happens to those? This goes here, and this goes here. And alas, they are linearly separable now in 2 dimensions. I mean, such an easy trick, very effective, right? I've just lifted them to 1 dimension higher, and now I could, for example, there are many, and you also see there's not just one hyperplane. These points here, these I could not linearly separate, these I can linearly separate. Nice trick. So you can always linearly separate by lifting to a higher dimension. One more thing, so these hyperplane things seem to work. A hyperplane in 1 dimension lower always divides the space into 2 parts. The one where the normal vector points, called positive ones, and the other one. What if I have more classes? Do I have more hyperplanes or what? Here's just, you don't need it for the exercise sheet, but you should know it. One is you can just build k binary classifiers. So assume you have k classes. Just for every class, learn a classifier like we do in the exercise sheet. Funny or not, thriller or not, science fiction or not. Then you can do multi-classification. Now the question is, what do you do when your one classifier says, yeah, it's funny, and also, yes, it's science fiction. Then you have to take the one with the higher score, but maybe their scores are not comparable because they are different classifiers. Or you play like a tournament, you compare all, so you classify, okay, is this comedy or science fiction? Is this comedy or horror? So you just play all pairs of classes labels against each other. That's a lot of pairs. Or whatever you do to learn your hyperplane, you somehow extend it so that it also can deal with more than 2 classes. So later we will talk about logistic regression. There is a multinomial logistic regression which can then work with multiple classes. So there's always extension of the theory, but we don't do that today, and it doesn't work for all methods. So for exercise sheet 11, we keep it simple. You just have 2 classes. For today, 2 classes. Okay. Before the break, one super simple method. Now we have seen the foundation. I think it was just some linear algebra. You know what classification is. How do you find such a hyperplane now? So that's what the second part of the lecture is about. So where is I don't see the pictures here. Just to clarify, so we are given our points now, and the task is to find this hyperplane, which, as we have seen, defined by just a W. How do I find this? How do I find such a W? And here's one method which is just so simple and is so surprising that it works. So you just iteratively compute the W. So all we need now is a W. The B, we got rid of that by just lifting to 1 dimension higher, so we just need to find let me just say that again. It's called W because the values are called weights for some, You typically call the values which you learn weights. That's the reason I will not go. So as I said, we will only consider hyperplanes. You can always do that by lifting 1 dimension higher with b equals 0. So we just have to learn a W. Makes everything simpler. So, and you just improve this step by step, hoping that you arrive at a good one. The Perceptron is from 1958, so it was already, and it's kind of the, like the core idea behind everything learning-wise. So you don't use the perceptron anymore, but you use some it's very similar stuff, and it's so easy that you learn something by seeing what it does. So let's just do the algorithm. You want to find a hyperplane. Let's start with a very stupid hyperplane, which doesn't even make sense. I mean, that's not even a hyperplane because it contains all the elements. So that's a degenerate case. But you can even start with that, or you can start with a random vector. You don't know anything. Now you go over the objects from your training set, over your examples, over your movie plots, one by one, and you do the following. You look at W, and let's just clarify what right prediction means. So right prediction means so this is greater or equal to 0, it's and the label is indeed plus, or your it says yes, this is negative, and the label is minus. So in that case, we do nothing. Then it's right. Yeah, we have our hyperplane now. We get it has a normal vector. We see a point, and we just check. Oh yeah, it's on the point. It's the right side of the hyperplane. So the hyperplane is fine for that point. We do nothing. Now comes if it gives the wrong prediction. So these are the other two cases. It says positive, it's on this side, but it's actually a negative one, or the other way around. Then you do the following. If it's wrong, so the sign of this is negative but should be positive, you just add the point to the weight vector. And this should look very strange to you. Adding, I mean, this is the normal vector, and now you're adding the input point. I mean, this doesn't make sense, really. But it's just super simple. And if it's the other way around, you have to decide what you do when it's exactly on the hyperplane. You can either do it here or there, or even do nothing. Then you subtract it from the W. That's it. That's the algorithm. So you just start with a random W, then you go through your points one by one. For each point you check, does it do the right thing for this hyperplane? Then do nothing. If not, do one of these two steps. And then you do that again and again. Note, important thing, you start with a random vector. You have 100 input points. You go through them in some order, ideally in a random order. And now you've done it for the 100 points, for all of them in some order. Now you have a different vector, right, than with the one you started with. So it makes sense to do it again. And that's also what you do in learning. And this is called an epoch. So you go over all your training samples one, but now you're in a different situation. You have a different W, and you're improving it iteratively. So now you can do it again, 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 with the same training samples. Yeah? You learned something, you went through all the slides of the lectures. Now you can start again and learn them again, because your brain is now in a different state. That's an epoch. Go over the training data many times. Okay, and that's what the perceptron does. Now there's a lot of theory behind the perceptron. We won't do that, of course, but just this one slide, why, and really you should think this doesn't make sense. Why does it make sense? So here's one intuition. But that's maybe not a very good intuition, and then I will give something more formal but very simple. So this is my hyperplane, and this is my normal vector, which defines the hyperplane, right? So this, on this side of the hyperplane, where the normal vector points are the positive examples, or are supposed to be the positive ones, right? And on the other side, I have the negative examples. Okay? So, if I have an object that's labeled, so let's assume, so I have here my x, which I'm now And it's, so here's my x. It's labeled, okay, how is it? It's labeled plus, but it's wrongly classified as minus. So let's say I have my x here, so this is my x, and it's here. That's what I'm writing here. But it's wrongly classified as... And then I'm saying it makes sense to correct w in the direction of x, yeah. Then maybe I should move the hyperplane a little over here, right? So that's the situation. I have an x here, which is actually plus, but my predictor says it's minus because it's on the other side of the hyperplane. Maybe I should move the hyperplane a little over here in the direction of this x. And this is what adding x does. And subtracting x says, so it moves the hyperplane closer to x or away from x. And let's, and if you look at the mathematics, actually very easy, but I think you need the combination of the mathematics and this intuition. So our current w says it's negative, but actually it should be positive because it's a positive label. Now, look what happens when I add the x. So I've already written it down here. Let's go through it step by step. So I'm now updating my weight vector, my normal vector as following. I'm shifting the hyperplane. So now the new prediction is this plus this. And now here I have, what's this? I mean, this is x square greater or 0. I mean, that's all the mathematics you need to see it. So if I add x, then the new prediction, so this value here will be larger than the old one. I'm adding something that's larger than 0. That's all you need to understand here. It was negative, it should be positive, and I'm adding something. So maybe it's still negative, but I'm making an improvement in the right direction, right? That's what I'm showing here. It said -3, it should be positive. Now I'm adding 1 maybe, or 1.5. Maybe it's still negative, but it got better. Maybe I didn't shift the hyperplane fast enough so that it's now on the other side, but at least I shifted it a little. That's what the perceptron does. And that's also what the other algorithms do. And the same goes in the, so the correction goes in the right direction. And of course, if you switch these two, then it absolutely, the sign here is very important. You have to make this little shift in the right direction. And here it's just the other way around. If it's positive, but it should have been negative, then you just correct in the other direction. And it's interesting that it's so simple. So that's all the intuition you need. And it's like the simplest algorithm ever. It can't possibly be any simpler, right? If you implement it, it's like, I don't know, 2 lines of code. And just to mention this, and then we have our break. So why does it even work? And again, you should stop and say, wait, this can't work because think about it. Let me look at this picture again. I get a training sample, it's on the wrong side. Now I shift my hyperplane. Now I get the next training sample, and then, now I shift it back because that's wrong. Why doesn't it go back and forth and cancel previous things out? I mean, even if you look at this algorithm, right? Why I'm going point by point, I'm making corrections. Okay, now it works better for this point, but maybe I destroyed everything I've done before. It's not at all clear why these things converge. And for the perceptron, it's so old, people had a lot of time to think about it. There is a convergence proof that if my data is perfectly linearly separable, that is, there is a line which perfectly separates the ones labeled plus and minus, then you can even give a bound on the maximum number of steps before it will find the perfect hyperplane. We don't do that theorem here, it's merely of historical interest, but at the time this was a big thing and not at all obvious. and nobody uses the perceptrons nowadays. We will now look in the last part after the break at a more principled method, logistic regression. And it's interesting, this is also interesting on a meta level. This is kind of, let me say this one more sentence. Oh, let me just try this. And oh, it works. And then let me try some, and yeah, there's an intuition for this, why this works, but this isn't very principled, right? It's like I'm coding something and it's the first thing that comes to my mind, the simplest thing that maybe works. And what we will do in the next part after the break is a bit more principled, and then it's interesting that you arrive at something which actually looks similar, but with a twist and works much better because it's just well-founded. So that's a nice experience on the meta level. And that is, the next part is 7 slides, but more mathematical, and afterwards that's it. So take a break and prepare for 7 more mathematical slides. See you. 7 more slides, but rather mathematical slides. Maybe the most mathematical slides from the whole lecture. But they have this super nice property that the formula in the end, the update step for linear regression, is super small, but you would have never come up with it yourself without the mathematics. So let's start with the sigmoid function. Who has heard of the sigmoid function before? Okay, great. So maybe that will be a nice warm-up. That's the sigmoid function. And these are also typical exam questions, which I show now. And anyway, good practice. The sigmoid function looks as follows. So I have it maps, and that's also why it's useful, any value to a value between 0 and 1. That is useful. It's for turning any value into probability. And it looks like this. Here. And then and this here is 0.5. 5, and that's sigma of x. So that's how it looks like. So what does it do? If you have values which are negative, if they are very negative, not even very large, then it's basically 0. If you have values that are quite positive, not even very large, it's basically 1, and a lot happens around 0. So if it's exactly 0, it's 0.5, which is basically I don't know. So negative is no, positive is yes. And let's look at a few properties. And let's maybe prove them. P1, and let me go back here. Yeah, this is, I think, let's prove some things here. So if so that's the function, and let me write it again as a fraction here. So the function is 1 to the 1 plus e to the minus t. Yeah, and I don't know, maybe when I write it, let me not write t, but let me write x, because the t always looks a bit like a plus. We can, of course, change the variable. Let's look at what happens if I go to minus infinity. Well, let me write it not quite correctly, but I mean that's okay in this case. What do I get when I have e to the minus infinity here? E to the minus infinity is 0, right? No, it should be minus infinity. Yeah, exactly. So I have 1 divided by 1 plus some very large number, and this is 0. Yeah, so this is not quite correctly written, but it is correct. And let's just do the sigma of x. So if I have 1 divided by 1 plus e to the minus infinity, now e for minus something very large becomes 0. So this is 1. Well, and if I plug in the value 0, yeah, you just have to plug it in. It's 1 divided by 1 plus e to the minus 0, which is e to the 0, which is 1, which is 1 over 2, which is 0.5. And it's also easy to see that it can never be less than 0. I mean, it's always non-negative. No way you get a negative number here. And it also can't be larger than 1, because this here is negative. Okay. That was a warm-up. Let's do the second property. That's interesting, and it will be useful in the following. Just some warm-up about the sigmoid function. So what is sigma, and let's do it with x, minus x. Let's just plug it in. It's 1 divided by 1 plus, it's e to the minus x. So it's now e to the x. And let's just multiply numerator and denominator by e to the minus x. And when I do this, now I get e to the minus x plus e to the x e to the minus x, 1. Now I have the numerator, denominator from this again. And now let me write this as, let me just add plus 1 and minus 1 here. Why not? E to the minus x plus 1. And now I have this part. I can now just write it as 2 fractions. This one here is 1. And the rest is, so that's now just 1 minus, and the rest is 1 e to the minus x plus 1 is, and that's just 1 minus sigma of x. And what this this also has an intuition in the graph. This just say that it's like symmetrical around this point here, right? If I want to know the value for, let me just show that here on the, if I want to look at the value for minus 3, and let's say 0.01, and I want the value here at 3, then it's 1 minus 0.01. It just looks exactly the same mirrored on the other side. That's what this says. So it's very symmetrical. And the third property, let's also prove that. And please tell me when I make a mistake. That's the derivative. It will be important in the following. So let's compute the derivative. And a lot of this here is recap of stuff which you should know, but maybe you forgot it or never really understood it. Now is the time to practice. So what's the derivative of 1 over x? That's 1 minus 1 over x squared. So now I'm using the chain rule here. So if I want the derivative of this, I first do as if this was just 1 over x. So it's just minus 1 over this thing squared. Yeah, and I could always say a lot about mathematics didactics. I didn't do it a lot in this course so far because we didn't have a lot of mathematics yet. But one important point, because I know that many of you are struggling with mathematics, maybe not those in the room, maybe those who are not listening, but anyway, the thing about mathematics is nothing is really hard, but if you're already struggling with more basic stuff, then it's very hard to understand more advanced stuff, right? If this is something where you have to think about for longer because your foundation is shaky, then now applying it in a context where you have a more complicated function and now need the chain rule and the inner derivative, the cognitive load just adds up. That's not one problem with mathematics. My claim is that's whenever somebody has problems with mathematics, that's it. When you even have trouble adding together fractions and thinking about, wait, when I add together fractions, what exactly do I have to do? And you need cognitive load for that, how can you don't have anything left for what is actually being taught. So, yeah, it's like stuff building on other stuff. And the way to go is, if you have problems, is always look for the level for where you have problems. Yeah. And if it's going back to basic arithmetic, maybe you have problems multiplying two numbers in your head, then that is where you should start. I think that's the single most important advice for getting. You can always catch up, but you have to go to the level, however low or not low it is, where you're having problems, and go from there. Because if your foundation somewhere is shaky, you can't build on it. Okay, that was Wort zum Sonntag. So we have to, we first compute this derivative, and now the chain rule. And let me at least write it here. So that's the, it's a bit small, but that's the chain rule. So now I need the derivative of the thing, which is, now I just did as if this was an x, but it's not, it's a function. So now I have derived this and multiply it here. The derivative of this is 0. The derivative of this, if it were e to the x, it's just e to the x, because it's e to the minus x. I have another chain rule, and I get another minus. And this is exactly what I was just saying. Maybe by looking up the chain rule you can do it, but it takes you 5 minutes, and that's a problem. This also, time adds up, cognitive load adds up. E to the minus x. Is that correct? And maybe I'm, yeah, maybe it's correct, maybe. And now something still is missing, right? I think I forgot something. Now I so much meta talk. Is this correct now? Minus times. Is it correct, or did I do something wrong? I'm not sure. Let's just continue. Okay, this is, let me write it like this. This is 1 to the 1 plus e to the minus x. I mean, I know where I want to go. Times, and then I have two minuses here, which cancel out. 1 plus e to the minus x, and this is actually sigma of x, and this is, I think we have already seen it above here. Yeah, this is just this one here. Right? It's the same. So we've already seen that it's 1 minus sigma of x. 1 minus sigma of x. So this is just, and that's, now you wonder what's the, so we've already proved this, we have proven this, and we have proven this. And this is relevant because the nice thing is, I mean, the derivative could be any complex function, but the nice thing here is, let's say I have something which evaluates the sigmoid functions, then the derivative, I can also evaluate it in terms of the original function. That's the nice thing about this. I could just also write what the actual thing is, like here, but I can express it in terms of the original function. Okay, this was the warming up, the 3 central properties of the sigmoid function, and let's move on. Here's some terminology. So D is the dimension of the input space. Again, we got rid of the B. We are only looking for a W. So it's that's why I gave it capital D here, and not, typically you don't do that, but just to avoid confusion. We started with a small d. Our capital D is just 1 dimension more. And here it should, of course, be not n, but d. I used to call it n. Okay. Now what do I have? I have my training examples, which are vectors. Let me very quickly maybe relate it to the, right? So for the exercise sheet, you have your text. Let's say you do it with embeddings. You do it with embeddings and with frequency vectors, but let's just talk about embeddings. So for each document, you just, for every word, you look at the embedding. If there is one, you just add them all up. You get a 300-dimensional vector for each object. This is how you always do it. Whatever you have, your objects, you somehow turn them into vector. That's what we did in the last lecture, it's what we do today, and what we will do in the last lecture. Yeah? So every plot becomes one vector now, the sum of the word embeddings. So this is my input, n vectors, and that's the things from which I want to learn. And for each of them, a label. Okay, why do I... Yeah, and the label is, okay, here I wrote it again for multi-class, because logistic regression can be generalized to multiple classes, but in the lecture, 2 classes. So for each, I just get 0 or 1, and it's actually exactly how it's written in the file. It's just 0 or 1, 1 is funny, positive 1, 0 is not funny. Okay, that's our input. I think that's easy to understand. And yeah, there is a generalization, but we won't do that today. 5 more slides to go, but mathematical slides. This one is also easy and nice, but maybe something you didn't fully understood in the past, so it's just a quick recap. Maximum likelihood estimation. And I deliberately did that to, yeah, I think it's important to... So if you have problems with that, again, go back to it, try to fully understand it. Simplest possible example, I think, to explain maximum likelihood estimation. I have a coin, and it's a biased coin, which means a coin which doesn't, it's not 50-50. It shows maybe head more frequent than tails, or the other way around. So let me just clarify this. So this is heads, so one side of the coin, and T is tail. Is it heads, head, tail, tails? I'm not sure, it doesn't matter. It's just two sides, 2 possible outcomes, and I just give them a name, H and T. So I cost the coin 20 times, and this is what I observe. So that's the situation in maximum likelihood estimation. I have an observation. And I have a model. I have a model, and it's a probabilistic model which makes an assumption on how this came to pass. And here the model is, okay, this is a coin, it has a certain probability to show up heads, and this probability is P. That's my parameter. If it were a fair coin, it would be 50%, but it's not necessarily a fair coin. Maybe it shows heads 10% of the time, but I don't know this P. So that's my model, and also, and I should write this here, independent. And that's what will also be, that's also implicit. So different tosses are independent. So the outcome of the third toss has nothing to do with the outcome of the first one or the fifth one. Independent. Now I can compute the probability, typically called the likelihood in that context. And I'm sorry that this is not blue. We can't continue before we make this blue. That's also easy. That's super basic. So what's the probability, given this model, what's the probability that this happens? Well, I do 20 times independent things in a row, so I'm just multiplying. Okay, there's 5 times heads, P times P times P, not in that order, but it's commutative, and 15 times this. So this is the probability of this happening. That's just how it is. That's very basic probability. Yeah. P to the 5, P times P times P 5 times, and this probability 15 times. And now the goal is, okay, that's my observation, that's my model, that's the probability of making that observation. What is the most likely model parameter? Yeah? What is the most likely P for that to happen? Or you could also ask, was it a fair coin? Is it likely that it was a fair coin when that happens? Probably not, because tail showed up much more frequently. And this example is so simple that we can actually compute it, and I will do that And on the next slide, you see an example which is also not super complex, but very quickly, when your model is not very trivial like this, you can't compute it anymore. But here we can compute it. So what do we want? We want, and I think there's one more. So I define this here as likelihood L of P. It's often called the likelihood. We want to find the P which maximizes this. I mean, that's a simple optimization. I think you also do that in school. I think you still do that in school. You want to find the P where this here is maximal, which means you somehow have to compute the derivative. It's not nice to compute the derivative of this. Think about it, right? Multiplication rule, it gets messy. Here's one thing which you always do. You want to find the P that maximizes this. You can also find the P that maximizes some strictly monotone function of this, like the logarithm. It's just the same. I will not prove it here, but whether you maximize L or log of L, because when the one is larger, also the other is larger, it's the same thing. You're not interested in finding the maximal value, you're interested in finding this P that maximizes this. So let's just do that. And if that's not clear, please take it home and try to prove this, that it's the same thing. So let's write down LF, N of LP, and you will see instantly, and that's a very typical situation. Likelihoods are usually products of probabilities, very ugly to derive, differentiate, ableiten. If you take the logarithm, it becomes a sum, much nicer. So now we have, and let me just write it down, ln of p to the 5 times 1 minus p to the 15. And now, just by the way logarithms work, that's now 5p plus 15. No, that's not true, of course. I'm sorry. 5 times ln p. That would have been 2. ln p, right, its product becomes sum and so on. It's ln p to the 5 times ln p, plus 15 times ln 1 minus p. And now let's derive this. And that's now much nicer to derive. That is 5 ln p, ln x. This is something also basic. Derivative magic power is 1 over x. And there's no chain rule stuff going on here, so that's just 5 over p. Plus, that's 1 over 1 minus p. Chain rule in a derivative is minus 1, so we have a minus here. Minus 15 of 1 over minus p. Okay. And now we don't have a lot of play, but I think it will be enough. We want to find the p. That's how you do it. You want to find the p that maximizes this, so you want to find the p where the derivative is 0, ln L of p prime is 0. So let's set this to 0. Let's do the following. F of p, that's 0 when these two are equal. 15 of 1 minus p. And that's equivalent. It's only equivalent when p and is neither 0 nor 1. Otherwise it's not equivalent and strange things happen. Let's multiply by p and by 1 minus p. Then I get 5 times 1 minus p is 15 times p. One more step, minus 5p, it's 5 is equal to 20p, I think. pp. And that's p is 1 over 4, right? So that's, and now I have also, I think also check, and let me maybe do that here. And we will not do it, but you can check it at home. that the second derivative, no, it's not small l, it's capital L, L of L, when applied to this 1 over 4 is negative, which means max, it's a maximum at 1 over 4. Yeah, that you also have to check. Otherwise could also be a minimum, but it's actually a maximum. So at P 1 over 4, and look, it makes sense. I mean, you might have said, yeah, I've seen that already. I mean, it's 3 times less likely to have heads than tails, so it's P 1 over 4, which means, by the way, that the opposite probability is 3 over 4, right? They have to sum to 1. So yeah, it's 3 times. So it's kind of the obvious thing, but you had to compute it. You never know, right? So if you see this observation and you have to make the best guess of the parameters, then it probably was a biased coin where the probability of showing heads was 1 over 4. And that's the way to do it. So here I could compute it exactly, but it's always that principle. That slide, in case you didn't understand that so far, is really important. It's a very simple principle, and for this simple example we can do the whole math with very basic methods. Any question about that before we proceed? And there are only 4 more slides, but they will become increasingly mathematical. So logistic regression also solves also does this, and I'm trying to make it analogous to the previous slide so that it becomes clear. So here my observation is a sequence of coin tosses. So here now my observation is I have my input points and my labels. So it's this is my observation. So I'm getting these movie plots and labels with them. And the thing is, but I can't help you with that. The assumption is always that this kind of happened according to some probabilistic model. But then again, our whole world happens according to a probabilistic model, right? Quantum physics is probabilistic. Deep down, everything is in a superposition of states, and when something interacts, something happens. So I think that's always confusing to people. Like say, wait, what? This is just given, it's fixed, but you assume a probabilistic model. This is something I think I cannot help you here. Can just say, think about it. Try to wrap your head around it, right? Again, the coin tosses, once they happen, they just happened, but there was some probabilistic process underlying it, and that's the model. So here, what happens. We have our movie plots with the labels, but some process led to it. And now the assumption is, and I only can give you a very bad intuition, but still it's an intuition. It's just a probabilistic model. The probability that the label is 1 for a point, and I think there should be an xi here. I'm sorry, let me just do that, and an xi here. I first did it without the, and that's also true here. Xi professional PowerPoint skills. So in case I always have second job. So that's the. And first check, without checking why it makes sense, that's a probability distribution, right? This plus this gives 1. And also sigmoid, that's the nice thing about a sigmoid, it gives you something between 0 and 1. This is a probability, this is just the opposite probability. So, yeah, so the labels were somehow created using this probability distribution. And now let's skip this, let's look at this. It's not easy to get an intuition for this model, but try to understand this. So I'm assuming, and it is worthwhile, I think, Now you could say, I don't care. Maybe you're one of those people, I want to just to see the mathematics, I don't care why this is the assumption, so I will compute with that. But I think it's worthwhile to think about it. But you have to do it yourself and at home. And by the way, do you also see that there? There's some cryptic writing up here. Where does that come from? Oh my, aliens. And just to give you a little help, so kind of what this model assumes is that I have my hyperplane as usual, and I have my normal vector W. And what is this here? This says, this is a value, we already know that's if it's on this side of the hyperplane, it will be a positive value on this side. And the further away it's from the hyperplane, it's the distance from the hyperplane, right? It's a large value. So what this is saying is, okay, if something is very far on this side on the hyperplane, it's surely 1. This is a value extremely close to 1. And you don't even, that's what the sigmoid function does, you don't even have to go far from the hyperplane. So that's kind of the assumption. I have a hyperplane on this side, if it's only a little bit away, it's almost surely the label is 1, and on the other side it's 0. And if I'm on the plane, then I get 0.5, and if I'm very close to it, it's also not so clear, but only a further away it becomes very clear. So kind of the best intuition for this model is you have this hyperplane, but these values are not probabilities, and the sigmoid function is just, you're looking for a way to turn things into probabilities. That's kind of the simplest way to go. It's a bit, if you think about BM25, that was also, we wanted formula with a certain property. Here's the easiest formula that does it. So it's a bit that kind of thing. But yeah, like quantum mechanics, you can think hours, days, weeks about what does it mean. And I think it's worthwhile to do it a little bit, but then you also have to just say, okay, these are the assumptions you have to carry on. I think it's important to say this because it's not that I don't understand why these assumptions don't make sense. Doesn't mean you're stupid. It's good to ask that question, right? Yeah, why? But on the other hand, these are the assumptions. Okay. Now, you can compute the likelihood just like before. Let me switch back and forth between the... If I have this model assumption, now I can compute the likelihood of this observation, right? Okay, I have a Toyn causes, let me just do this. And let me just do this here. The formula is now a bit more complicated, but actually it's very nice here. And also let me say this on the meta level. It's really important for mathematics. Yes, at certain points try to get an intuition, but then sometimes just compute with what you have, right? Ignore the intuition and just do the math. And that's what we will do here. Okay, let me just compute it and see what comes out, whether I understand it or not. So this probability here is, let's just write that. The probability for a label yi is, and it's kind of, I have two cases, right? If yi is 1, then it's sigma times w times xi. I'm just copying what's written up there. If yi is equal to 0, then it's the opposite, 1 minus. Now that's not nice, right? If you compare it again to the previous slide, here I didn't have such a thing. This probability was, now I have a case, if it's this label, it's that. If it's that label, it's that. And the nice thing is I can write this as 1. And that's very strange, but yes, I can do it. Yi times 1 minus sigma 1 minus yi. It's strange, but it's true. I mean, just plug it in. If yi is equal to 1, then 1 minus yi is 0. This disappears. I get this one, which is this case. If yi is equal to 0, then this here disappears. Something to the 0 is 1. And this here is 1, and I get this term. So I have this case distinction, and I can just turn it in one expression, which moreover I can differentiate now, derive, ableiten, right? And this is what I get here. So the probability of this here now just, so the probability for a single sample becomes this. It would not be nice to compute, otherwise I would have to write, I mean, like this, I just have one closed expression, right? It's really nice that I can do it like this. And it's trivial. I mean, that this is equal to this, you can trivially check. It's just funny that you can do it. And then, yeah, independently, again, I have an independence assumption. I do it for every sample point, so I just multiply the probability. So that's my likelihood here. And as you can see, it's now slightly more complicated than the one on the previous slide, but it's in principle the same thing. That's what I did these two. Here, my model parameter is the p, and that's my likelihood. And here, of course, I have a fixed example. I didn't say so many times head, so many times tail, then I would have 2 more variables in here. So here it's a bit more abstract. So here I also have the sigmoid, and I have vectors and not just scalars. So more complex on multiple levels. But the task is the same. This is a probability, and now I want to find the W that maximizes this. So when you look at this at home or prepare for the exam, go back and forth between these two slides and to see that it's the same thing, just more complex here. So now our task on the next 2 slides will be to just try to solve this problem. And here's the... So, and again, same trick. We don't take the likelihood because deriving a product of strange things is not nice. Let's just take the logarithm as usual. Yeah, instead of trying to find the W that maximizes this, find the W that maximizes the log of this, which is the same thing, same reasoning as before. Now, so that's our task. Given this, find the W that maximizes this. This looks very hard, and indeed, you can't do it. Let's again go back to this slide. This you could solve. Find the P that maximizes this. We could do it. Logarithm, derivative, 1/4. That was easy. And even if you don't have 5 and 15 here, but M1 and M2, you will get M1 divided by M1 plus M2. That's what you get here, right? It's basically 5/5 plus 15. So that was easy. And that's what you typically do. In all of learning and all these problems, whenever you want to have such problems, you can't compute the exact solution with a closed formula. You do something iterative, just like for the perceptron. But now, not with some rules which just came to your mind during sleep or not sleep, but we do it more principled. So again, you start with some W, and now in each step you compute the gradient. Now why do you do that? That's actually also not hard to understand, and you maybe have already seen this somewhere. Let me do it in... and now I'm drawing, I can't draw a 1D, 2D landscape, so I'm drawing a 1D landscape, which is just a function here, right? So I'm here at my W, and now I'm looking for the maximal value in that landscape. And the comment I made here is to think about it, and let me just make this here a capital R, a boldface R, sorry. The picture I want you to see here is, think of my weight vectors are now, but I can't draw it, so my weight vectors are now here a plane, and now I have some landscape here. I can't draw a 2D landscape very well. Just think about a 2D, you have the plane like the Earth, and now you have a landscape there, and you want to find the highest point, right? That's what you want to do. And now you are at a certain point. Why is this not working? You are at a certain point. And now you just look at, okay, the direction of steepest ascent, and that's the gradient. That's if you compute the partial derivative at that point. So, and for the one dimension lower, you just compute, if you compute the derivative here, it will give you a direction, and it just say, go in that direction, you will reach higher points. And go in the direction where you reach higher points the fastest. And you can do the same thing in 2, 3, and more dimensions. You are somewhere in a landscape, go where it goes the steepest uphill. And now that's what we will do now. We will do derivative in higher dimensions, which is just partial derivatives. It's also conceptually easy. And this gradient just gives you the direction of steepest ascent. So that way, we don't have a closed formula for finding the highest point, but at least we can try to get there by always climbing upwards. So, now comes some nice calculus, and it's only one slide to go. The next slide is easy, and it's the last one. And let's do the mathematics. It's very nice, and also the thing here is, this is really very simple derivatives, but now you are in not in one dimension, but in multiple dimensions. And you can actually see it here. I mean, if you compute it, this is now a vector product, right? And let me maybe just, I think, let me spend that 1 minute because it's worth it. So this is our W, and maybe it has, yeah, we know it has d dimension, and this is our X. And it also has d dimension. Then the scalar product is just the sum of these things, right? Wi times xi. And now I'm taking the derivative of this thing. And let me just take the derivative with respect to one of these components, Wi, right? Now I have the sum of these Wi, xi. I mean, everything is constant now except for maybe it's the W5, right? So I just get W5 times X5. All the others are constant terms now when I derive with respect to W5. And what happens if I have W5 times, and the xi is also, it's not a variable. So yeah, it's just xi. If you derive 5x by x, you get 5. You get the factor. So this is just Wi. And when you do W, and that's just the definition of, if you now derive by the partial derivative here by the whole vector, then it's no xi, not Wi, thank you. I said it right and wrote it wrong. And if you just do this for all of them, you just get xn, which is the x again. So it's actually, it's trivial, but you have to lift it to the higher dimension. And the funny thing is, so, I mean, if this were all scalar numbers, computing, and this is just normal multiplication, then this is obvious. The derivative of 5x is 5, but you can just also do it with vectors. And here's the proof. So even lifting this to higher dimensions is not hard. You just take the concepts which you know from one dimension and lift it to higher dimensions, and then it works. So this we have already proven here. And of course, I mean, you can just do it and assume that it works, or try to convince yourself that this is true. And so now let's just do as if these were normal numbers and compute the derivatives. So we have, yeah, this here, I don't think I will do the math again. Let me just go to the if I do the logarithm here, then it should be, maybe let me very quickly do the beginning, right? If I, this is now, the product becomes the sum, as usual, 1 over n, and now I have ln of this, which means yi times ln of sigma, I don't need these parentheses, and so on. I will not write the whole term. Sigma of w times xi plus, it always looks like this. You have this product, and then the logarithm of the product becomes the sum of these things. Yeah, and that's what I have already done, and we have already seen it once for the, so the log likelihood, and I think this should not be L, but I think I called it, yeah, this is actually my ln L, so that's what I optimized, but let me now just call it L, it doesn't matter, I could also use this simple symbol for that. That here, we have already established, we have even proved it, the derivative of the sigmoid is this. I mean, we want to compute derivatives here, we have the sigmoid, we certainly need the derivative of the sigmoid because of chain rule, and this we have just proven. So, let's just do it. Let's do it. And again, now's the time, maybe you have some intuition for it, maybe not, now just do the math. Yeah, that's very important when doing mathematics. Take your time to understand the mathematics, intuition, but then also, okay, now let's just compute. Let's just take this monster here and compute the derivative. And that's, okay, I have to make this one favorite remark of mine. This is like divided by 4 plus 15 to the power of 3 minus 7. Is this hard to evaluate? Yes and no. I mean, it's complex, you have to do it, but it's not really hard, right? If you know how to multiply, subtract, divide, and take to the power 2, you just do it. It's just complexity by having a lot of it. It's exactly the same here. Every single thing is simple, like here. But it's just, oh, I have to compute the derivative of this. So it's, let's do it. It's the last thing we do. And it's a lot of fun actually. So let's compute this dl of dw, and you, yeah, I don't have. So let's do it. So it's we derive by dw. So it is the sum of I 1 to the n. It's yi ln of, okay, so that's yi times 1 over this thing. xi, 1 over xi, now I have to compute the derivative of this thing, chain rule, right? Again, chain rule, 1 over this, ln x, 1 over x, chain rule. Derivative of this thing is this thing. And then I even have the derivative of this inner thing. So multiply with this, and then the derivative of this thing. I just do it. So I get the derivative of sigma times xi times 1 minus, that's the derivative of this, and one more chain rule times the derivative of this. This was the derivative of just sigmoid. There's not x in w in here, but w times something. The derivative is this, so times xi. Of course, very easy to make a mistake here. Times xi. And so nice, something cancels out here, right? Cancels out. And now plus, so we just do the same thing for the next term and see what happens. Plus, and it's still part of the sum, plus 1 minus sigma I times 1 to the derivative of this, 1 minus sigma of w xi. Now, derivative of this. Oh, it's 1 minus, I'm confused myself. How do I derive how do I derive this? Oh, this is actually, I should say this, it was on the previous slide. This is equal to sigma of minus. I think that will be easier if we do it that way. 1 minus or sigma of minus is this. It was on the previous slide. So let's do that. So then now we have the same thing. Now we have sigma of, oh, now I have a lot of minuses. Sigma of minus, times 1 minus sigma of, oh, now I lost track of the minuses, times okay, I think I have a minus here now, minus xi. I think I do. Okay, anyway. If not, I will just pretend it's the other way around so that it works, but just for the lecture. So let's see what comes out is equal to I equals n 1 to n. It's always a sum over these things. It already simplifies quite a lot. yi times 1 minus sigma xi times xi minus 1 minus yi times sigma xi times xi. And I think more stuff cancels out, I hope, right? Does it? yi minus... Yes, please.
You said earlier that like 1 minus sigma w times xi is the same as sigma minus w times xi.
Is it?
Then we have to.
Yeah, is it not true? I hope.
No, I mean it can be true. That's not.
Yeah, it was this one here, P2, right? Yeah, that was this. Yes.
Yeah.
And then I made a mistake, probably. Yes.
Actually, yeah, but then when we substituted this, we didn't carry the minus.
Yes, you're right. I think we get the minus probably twice here, right? I mean, it doesn't, I know what you mean, but it doesn't matter. If we have the minus twice here, it's still the same thing, right? This here, with a minus,
we can resubstitute then, yes.
yeah, it becomes the same thing. But what I'm confused now is I think I need another, do I need another minus here or not? I don't think we have time to resolve it for reasons of time, but let me just... But you are right to point out that there was something where I lost over here. So this is still correct, but because even if I put a minus here and here, the product is the same thing.
Instead of the minus missing in 1 divided by 1 minus sigma of something, there should be a minus before it because we have a minus w on top.
Yeah.
So we do ln of 1 minus sigma of
Yes.
times, and there should be another minus.
There should be another minus where? Coming from where?
From the derivative of ln 1 minus sigma of w times xi.
Yeah, I think so too, but I'm a little bit confused now. So I think you are right. Let me just, I think what I... Let's just see whether this last equality holds here. yi minus Yeah, I mean this cancels out, that was true. Yeah, maybe there are 3 minuses here or 1 minus, one of them is true, so this also cancels out here. Right here I have yi minus sigma of this, and here I have plus yi sigma of this, so this also cancels out here. I can't really write it that way, I would need an intermediate step. But anyway, I think, so a little shaky here, but that's fine. Anyway, you have to do it yourself too. So, yeah, please do it yourself and pay attention to the minuses. And sorry that I can't fully resolve it now. So there are a lot of minuses here to keep track of, and I was a little quick here, but that is, I think, yeah, that is what I wanted to get as a result. So either there's 1 minus here or there are 3 minuses here and effectively 1 minus. Let's go to the next slide, which is the last slide. So this is what comes out, and now let's just apply this not for all the points, but just for 1 point. Then what do you get? Now I'm just, yeah, let's just go back to one slide before. I'm correcting my W in the correction of the gradient. I've computed the gradient. Let's just do it for 1 point. And now I get this. And then how much do I go in the direction of the gradient? That's just a factor which we call the learning rate, right? I see this direction. Now how much do I go there before I re-evaluate? Maybe 0.1, 0.01. It's a parameter. It's the learning rate. So now I get this, and note what we had for the perceptron, right? Let me just write it here, and then we are almost done. For the perceptron, we had W plus X or W. I mean, all this complicated, not so easy mathematics, and now you get something very similar, but you have this factor in front of the x. It's y minus sigmoid of, I mean, how should you have come up with that yourself without theory, right? And that works much better. So you're also going in the direction of x, but with this factor here. And here you have the, depending on the label, you will go positive or negative direction. But it looks very similar to the perceptron, which is interesting, with a twist. And the last thing, and then we are done. So here we did it for all the samples, so you sum up the gradients for all the samples. It's a sum over all my input points. Here I just did it for 1 point. How you actually do it in practice, I will not explain why, is you divide your input into batches of equal size. Can't be fully equal because maybe you have 117 inputs and your batch size is 20, then one batch will be smaller, but let's just assume. So here I have a batch, so I'm just summing this up for all things in my batch and divide by the batch size. So yeah, that's very easy. It's really very easy. I have this gradient thing here, and now I just take 20 of my movies, 20 of my objects, compute it for each of them, this thing here, which is easy to compute, hard to prove, easy to compute, and take the average. And then I go, just change W a bit in that direction. Yeah? And experiment yourself with batch sizes. It's just a parameter in your code. Let me just summarize. There are 3 parameters now. The learning rate, how much do I go into the direction of the gradient. The batches, how many at once before I make a correction of my W. 10, 20, 100. And how often do I go over the training set, number of epochs. And that's the typical hyperparameters you have. And last word, so that will be your task to implement that. The formula is simple. How do you implement that in linear algebra? You can do it in very few lines of code. It's very interesting to understand what you're doing, also getting used a bit more to PyTorch. So that's it. Any questions about this? Please do the exercise sheet. Please do the evaluation if you haven't done it. Thank you. See you next week. Bye.